Case 1. The galaxies that formed too early. The early universe. Observations from 2022 to 2023. According to the standard cosmological model, the universe after the Big Bang was a simple place: hydrogen, helium, darkness. Then, gradually, over hundreds of millions of years, the first stars ignited. Galaxies assembled slowly from clouds of primordial gas, growing through mergers and accretion like cities built brick by brick across geological time. The James Webb Space Telescope looked back to that era and found something else entirely. Massive galaxies, fully formed, structured, rotating, existing only a few 100 million years after the Big Bang, when the universe was barely 3% of its current age. These weren't small clumps of stars. They were galaxies nearly as massive as the Milky Way, complete with organized spiral arms and dense stellar populations that should have required billions of years to develop. The timeline doesn't work. There simply wasn't enough time for that much matter to collapse, ignite, and organize itself into coherent structures. It's like finding a skyscraper in a neighborhood where construction permits were issued last week. Astronomers initially suspected measurement errors. Perhaps the galaxies were closer than they appeared, their light redshifted by some unknown mechanism, but repeated observations confirmed the distances. These galaxies existed when the universe was impossibly young. Some researchers proposed that the galaxies weren't as massive as they seemed. Maybe supermassive black holes at their centers were amplifying their brightness, creating an illusion of size. Follow-up studies found this explained a fraction of the discrepancy. But even after accounting for black hole contamination, roughly twice as many massive galaxies remained in the early universe than the standard model predicts. The physics doesn't allow it. Dark matter, which provides the gravitational scaffolding for galaxy formation, can only collapse so quickly. Gas can only cool and condense at certain rates. Stars can only form when specific conditions are met. Every step in the process has a speed limit determined by fundamental physical laws. Yet the galaxies are there, fully assembled, defying the clock. One possibility is that star formation in the early universe was far more efficient than current models assume. Typically, only about 10 to 20% of available gas converts into stars. The rest is blown away by stellar winds or remains unconverted. But some of the early galaxies observed by JWST appear to have converted nearly all their available gas into stars, achieving efficiency levels that shouldn't be possible. This raises a question that cosmologists are reluctant to ask. What if the early universe operated under different rules? Case 2. The impossible brightness problem. Deep Field Surveys, 2022 to 2024. When JWST began its deep field observations, astronomers expected to see faint, distant galaxies struggling to shine through the cosmic fog of the early universe. What they found instead were objects so bright they seemed to violate the limits of stellar output. These galaxies weren't just unexpectedly large. They were radiating far more light than their estimated mass could produce. Even after accounting for the most optimistic assumptions about star formation rates and stellar populations, the brightness remained inexplicable. Simulations of galaxy formation are built on well-tested physics. You input the initial conditions of the universe, the distribution of dark matter, the behavior of gas under gravity, and the code evolves forward in time. When you run these simulations and look at what they predict for the early universe, you get galaxies that are smaller, dimmer, and fewer in number than what JWST observes. The discrepancy isn't subtle. It's a factor of several times in both brightness and abundance. One explanation involves feedback mechanisms. When massive stars die, They explode as supernovae, blasting gas out of their host galaxies and temporarily halting star formation. This negative feedback is supposed to regulate galaxy growth, preventing them from becoming too massive too quickly. But if feedback was weaker in the early universe, galaxies could have grown faster and brighter than models predict. Except there's no clear reason why feedback would have been weaker. The physics of supernovae doesn't change with cosmic time. Another possibility is that the initial mass function, the distribution of stellar masses when stars form, was different in the early universe. If the first generations of stars were more massive on average, they would have burned brighter and died faster, potentially explaining the excess luminosity. But this introduces its own problems. Massive stars produce heavy elements when they explode. If the early universe was dominated by massive stars, we should see higher metallicity in ancient galaxies. We don't. The observations sit there, unreconciled with theory. Case 3. The dust that should not exist. Early galaxies and supernova environments, 2022 onward. Cosmic dust is the ash of dead stars. When massive stars explode, they forge heavy elements in their cores and scatter them across space. Over time, these elements cool and condense into tiny grains, particles of carbon, silicon, iron, and oxygen that absorb starlight and glow faintly in the infrared. Dust takes time to accumulate. It requires multiple generations of stars to live, die, and seed the cosmos with raw materials. In the early universe, where stars were just beginning to form, astronomers expected to find very little dust. The conditions were too harsh, the stellar populations too young, the heavy elements too scarce. JWST found dust everywhere. Not trace amounts, substantial quantities, enough to obscure starlight and reshape the appearance of entire galaxies. The volume of dust observed in some early galaxies rivals what we see in mature systems billions of years older. This shouldn't be possible. Dust production mechanisms are well understood. You need asymptotic giant branch stars, the dying phases of sun-like stars that puff off their outer layers and produce carbon-rich grains. But these stars take 1 billion years or more to evolve into that phase. In the early universe, there simply hadn't been enough time. Supernovae can also produce dust, but they're inefficient. Most of the dust they create is either destroyed by the shock wave itself or swept away by radiation before it can accumulate. To explain the dust levels JWST observes, you'd need an implausibly high rate of supernovae occurring in rapid succession, each one somehow preserving its dust output against intense ultraviolet radiation. Some researchers suggested that the dust might not be dust at all. Perhaps it's a different form of carbon-based material, something like graphite or diamond grains that form through unknown processes. But spectroscopic analysis confirms the presence of familiar dust signatures. This is the same stuff we see elsewhere in the universe, just appearing far earlier than it should. The dust is there, dense, widespread, existing before the mechanisms that create it had time to operate. Which means either dust forms through pathways we don't understand, or the early universe was aging faster than the laws of stellar evolution permit. Case 4. The missing first stars. Primordial universe. Ongoing JWST surveys. The first stars, known as population 3 stars, were supposed to be monsters. Formed from pure hydrogen and helium in the pristine conditions of the early universe, these stars would have been hundreds of times more massive than the Sun, burning with such intensity that they would have ionized vast regions of space and died in spectacular explosions within a few million years. Their existence is foundational to cosmology. They're the source of the first heavy elements that should have seeded the universe with everything that came after. Without them, the cosmic timeline collapses. JWST was designed in part to find them. It hasn't. Not one confirmed detection. Not a single spectroscopic signature matching the predicted characteristics of population 3 stars. No metal-free stellar atmospheres. No ultramassive remnants. No direct evidence of their existence anywhere in the observable universe. These stars should be everywhere in the deep past. Their light, red-shifted into the infrared, should be one of the clearest signals JWST could detect. Instead, the telescope sees galaxies already enriched with metals, already structured, already populated by second- or third-generation stars. The absence is profound. Without population 3 stars, you lose the seed mechanism for everything that follows. You lose the first heavy elements, the first supernovae, the first ionizing radiation that cleared the fog of neutral hydrogen and allowed the universe to become transparent. You lose the foundation. Some researchers argue that these stars existed, but were simply too short-lived to detect. Others suggest they were far less massive than expected, making them too faint to observe even with JWST's capabilities. But the absence is glaring. After years of searching, the stars that should define the early universe remain invisible, which raises a disturbing thought. What if they never existed at all? What if the first light in the universe came from something else entirely? Case 5. Star formation that defies its own rules. Nearby and distant galaxies, 2022 to 2024. Star formation follows a pattern. Gas collapses under gravity, clouds fragment, protostars ignite. The process is gradual, regulated by feedback from stellar winds, radiation pressure, and supernova explosions. This feedback prevents runaway star formation, keeping galaxies from burning through their gas too quickly. It's a balance. A cycle of birth, death, and renewal. JWST observed galaxies where this balance doesn't exist. Some galaxies are forming stars at rates far exceeding what their gas reserves should allow. Others sit dormant despite having abundant fuel. The discrepancies aren't minor. They're systematic. In one group of galaxies, star formation efficiency reaches nearly 100%. Almost all available gas is being converted into stars, a process that should be impossible. Stellar winds, radiation pressure, and supernova feedback are supposed to expel gas and regulate star formation. But in these systems, the gas isn't leaving. It's being consumed. In other galaxies, the opposite occurs. Vast reservoirs of cold molecular gas sit idle, producing almost no stars. The conditions are perfect. The raw material is abundant, yet nothing happens. These are not isolated cases. JWST has observed galaxies across different epochs that behave inconsistently with star formation theory. Some appear to violate the Kennicutt-Schmidt law, the fundamental relation linking gas density to star formation rate. Others form stars in environments that should be too chaotic, or fail to form stars in regions that should be ideal. What ties these anomalies together is their unpredictability. The same physical conditions produce wildly different outcomes across different galaxies. The models that successfully describe star formation in the modern universe fail when applied to the early cosmos. Either the rules have changed, or the rules were never as universal as we believed. Case 6. The ice chemistry that appeared too soon. Dense molecular clouds. 2023. Chemistry in space is supposed to be slow. Cold molecular clouds begin simply. Water ice on dust grains, carbon monoxide in the gas, a handful of basic reactions ticking forward over long timescales. Complexity is expected to come later, after stars ignite, after planets form, after energy and stability allow chemistry to build upward. JWST looked into dense molecular clouds and found complexity already waiting. Ice grains loaded with organic compounds, chemical structures that, according to standard models, require stable environments and long timescales to develop. Yet they were embedded in regions that had barely begun forming stars. The implications are unsettling. If complex organic chemistry appears this early, it suggests the building blocks of life may not require the slow, gradual progression we assumed. Either the chemistry is faster than we thought, or the environments we're observing are older than they appear. Both options strain the timeline. Worse, some of these molecules shouldn't survive where they were found. Ultraviolet radiation from young stars should tear them apart. Yet they persist, stable and abundant, as if protected by mechanisms we don't yet understand. Case 7. The carbon-heavy atmosphere of WSP-39b. Observations released 2022. When JWST turned toward WSP-39b, astronomers expected refinement. A clearer measurement of an atmosphere already broadly understood. Instead, JWST delivered a chemical inventory that didn't fit the predictions. The atmosphere was loaded with carbon dioxide and sulfur compounds, and the spectrum revealed a level of molecular detail previous instruments couldn't approach. It wasn't just detection, it was clarity. A fingerprint so sharp, it left no room to argue the signal was noise. Models predicted simpler behavior under intense stellar radiation. Instead, JWST observed an atmosphere that looked active and chemically complex, shaped by photochemistry and reactions driven by starlight in ways that challenged standard assumptions. This wasn't a failure of observation, it was a failure of expectation. The data didn't force a minor correction. It forced a reconsideration of how we think planetary atmospheres work. Case 8. The Flat Atmosphere Mystery. Multiple exoplanets. 2023 to 2024. When astronomers study an exoplanet atmosphere, they look for spectral lines, the dips and patterns that reveal water vapor, methane, carbon dioxide, and other gases. Even a thin atmosphere should leave a trace, a signature, a structure. JWST found planets where the spectrum is nearly flat, featureless, smooth curves where the fingerprints of molecules should be obvious. It's not a weak signal, it's an absence. At first, thick hazes seemed like the answer. High-altitude clouds can scatter light and hide absorption features. But in some cases, the flatness is too complete, too uniform, as if the atmosphere is either completely opaque or not behaving like an atmosphere at all. The unsettling part is what the data implies. Either these planets are hiding their chemistry behind processes we don't understand, or the composition is something outside the models we rely on. The telescope is looking directly at alien skies and seeing nothing it recognizes. Case 9. The Silent Worlds of TRAPPIST-1. Observations released 2023. The TRAPPIST-1 system was once considered a prime target for habitability. 7 rocky planets, several in the habitable zone, close enough that JWST could attempt to probe their atmospheres directly. If any nearby system could reveal Earth-like air, this was the one. The results were quiet. JWST observed several TRAPPIST-1 planets and found no evidence of thick atmospheres, no clear signs of carbon dioxide, no water vapor, no protective envelope of gas. The spectra suggested exposed surfaces, worlds stripped down to rock. Red dwarf stars are violent compared to their size. Flares and radiation can erode atmospheres over time, and TRAPPIST-1 may be doing exactly that. If rocky planets around red dwarfs routinely lose their air, then habitable zone becomes less a promise and more a warning. and red dwarfs are the most common stars in the galaxy. If TRAPPIST-1 is normal, then the universe may be full of planets, and far emptier of worlds that can stay alive. Case 10. The Quiet Crisis in Cosmology. Across multiple JWST datasets, 2022 to present. No single JWST discovery breaks the standard cosmological model. Each anomaly can be explained, at least on paper, with adjustments. Increase star formation efficiency. Invoke early black hole growth. Accelerate dust production. Tweak assumptions, and the model survives. But the anomalies don't arrive one at a time. They appear together, across different epochs, in different environments, observed through different surveys. The pattern is what matters. JWST was supposed to refine cosmology. Instead, it has exposed cracks in the foundation. Structures appear too early. Chemistry advances too quickly. Star formation behaves unpredictably. Atmospheres vanish or hide. The early universe looks developed before it should be able to develop. Each fix creates tension elsewhere. Solve one problem and another sharpens. Explain early galaxy mass, and you strain dust production. Account for brightness, and you destabilize stellar population assumptions. Narrow habitability, and you make life statistically fragile. The model isn't collapsing, it's fragmenting. It still explains the universe in broad strokes, but the details are increasingly incompatible with what JWST is showing. The crisis is quiet, because admitting it would mean rethinking decades of confidence. Cosmology rests on assumptions that the universe is uniform on large scales, that the laws of physics are constant across time, that the framework connecting expansion, structure, and matter is fundamentally correct. Those assumptions weren't chosen lightly. They were built from data. But JWST is testing them deeper than any telescope before it. And the deeper it looks, the less the universe resembles the one our models describe. The early galaxies keep appearing too massive. The stars keep forming too fast or not at all. The chemistry keeps arriving too early. The atmospheres keep vanishing. The contradictions are persistent, not occasional. The telescope keeps observing, and the quiet crisis keeps growing.